Hello, this is Shafi. My project is Bacterial image detection for AMR based on deep learning methods. The main aim of the project is to develop an automated system that effectively recognizes various bacterial species from microscopic images and predicts which ones are resistant to which antibiotics using deep learning techniques. Here, this is the code I have done. So, firstly, we need to check the GPU status in the system. So, we are running this command. This shows the directory where the notebook is located. This installs the latest version of the Ultralytics package from PYPL. This includes YOLO version 8 and other handy tools by Ultralytics. Next, this line clears the installations logs output to make the notebook cleaner. Next, this imports the Ultralytics library and runs a series of environment checks. Example, PyTorch, Python series versions, Python versions to ensure everything is set up correctly for training. Next, we are cloning the GitHub repo named bacteria detection. In the next line, lists the contents of the current directory because it is useful for verifying that my files are present. This installs Git large file storage, Git LFS. Git LFS is needed if your cloned repo stores larger files like model weights through Git LFS. So now we change the working directory to the cloned GitHub repo and downloads the large files that are tracked by Git LFS. Next, we are trying to display the contents in the directory. Now I am using wget to download a .zip file directly from a GitHub repo and downloads the classes. The files from the downloads folder of the bacteria detection GitHub repository. After downloading, we unzip the dataset file from here. This course loads a YOLO version 8 model, performs object detection on a given image, and extracts bounding boxes and confidence scores and class IDs, and then draws the bounding boxes and labels on the image using OpenCV. Finally, it displays the annotated image in the Collab notebook using CV2, I'm sure. Next, we initialize the YOLO version 8 model by choosing YOLO version 8N or YOLO version 8S. Print model summary info and then view the model architecture, lit- literate through individual layers if needed. The command YOLO trains a YOLO version 8 object detection model using a pre-trained YOLO version 8 model and dataset specified in data.yml. The model will train for 100 epochs, resizing all input images to 224 into 224 pixels to optimize training speed and memory usage. The data.yml file contains crucial information about the dataset, such as image paths and class names. The plots equals to true option generates visualizations of training metrics like loss, precision, recall, and MAP2 monitor model performance during the training process. This setup enables efficient and informative model training, allowing you to fine tune YOLO version 8 for your custom object detection task. This code uses Optional to optimize YOLO version 8 training hyperparameters by running multiple trials, each with different parameter combinations. It trains the model via subprocess calls and evaluates performance based on MAP at the zero point 0.5 extract from the logs. The best performing hyperparameters are identified and printed after all trials. The command YOLO is used to perform object detection on a set of test images using a previously trained YOLO version 8 model. The model specified by the path is used to predict the presence of objects in the images located in the test images directory. The configuration equals to 0.555 parameter sets a confidence threshold of 55%, meaning only predictions with a confidence level above this threshold will be considered valid. This command is used to evaluate the model's performance on Neo and sync data by detecting the classifying objects based on training it has received. So now all the results are saved in the runs folder. Uh, it specifies the path to the image generated during the YOLO version 8 object detection predictions and then uses the display function with the image class to render the image inline. This approach allows you to view the detection results directly within the notebook, making it easier to analyze the performance of the training model on new data. The confusion matrix illustrates that performance of a classification model across four categories dividing microcolony, rod, and background. The diagonal values represent the number of correct predictions for each class, while the off diagonal values indicate misclassifications. The model correctly identified 74 instances of dividing, 37 of microcolony, 97 of rod, and had no correct predictions for the background class. Overall, while the model performs reasonably well in identifying rod and dividing, there is significant room for improvement in distinguishing background and reducing cross-class confusion. This F1 confidence curve shows how the F1 score varies with the model's predictions confidence for different classes. Each line presents a class dividing microcolony and rod. From the graph, we can see that the model achieves its optimal F1 score for all classes is 0.80 at a confidence threshold of 0.564, marked by the bold blue curve. The PR curve shows the balance between precision and recall for each class, with microcolony achieving the highest score of 0.887. The overall MAP, the zero point 0.5 is 0.862. It's indicating strong model accuracy across all classes. We can see this precision confidence curve shows how precision changes with confidence threshold for each class. The model reaches perfect precision 1.0 for all classes at a high confidence threshold of 0.993. It indicating high confidence predictions are very reliable. This recall confidence curve shows how recall decreases as the model's confidence increases for the dividing, microcolony, and rod classes. The microcolony classes orange retains higher recall at higher confidence levels compared to others. The thick blue line indicates overall recall across all classes. Starting at 1.0 when the confidence threshold is 0, this helps evaluate how many true positives are retained at different confidence levels. Next, here we are displaying the detection for the microscopic image in the batches. Summary of the YOLO version 8 model highlights some key takeaways. Here, overall performance, the model is showing strong results with an overall precision of 0.83, recall of 0.688, and MAP of 0.821. The model performs quite well, especially considering it's handling multiple classes. Whereas in micro colony class, this class is performing exceptionally well with precision of 0.926 and recall of 0.85, which means the model is both very accurate and consistent in detecting this class. It's a standout class in terms of detection quality. For the rod class, the precision of 0.846 is good, but the recall of zero point 0.6 is relatively lower. This suggests that the model might miss some rod instances, even though the predictions it makes are generally accurate. This class could benefit from better recall, meaning the model could be more sensitive to detecting rod instances. And finally, when it comes to dividing class, this class is the weakest with a precision of 0.72 and recall of 0.615. It's indicating the model struggles the most with detecting dividing instances accurately and consistently. Its improving performance on this class would likely be a key focus for further model refinement. So now coming to deployment, I have created a web application using Flask. So now I'm going to upload an image to detect bacteria. So so if I upload any image and click on the detect bacteria button, It detects all the rod, microcolony, and dividing in the image. So I have uploaded the image now. You can see it. It's showing microcolonies, dividing, unrod, everything in this image. So what I'm going to do is I am going to upload another image as well. Let's see. So now I'm going to select this image, detect bacteria. So now you can clearly see that in this image as well, it's clearly detects microcolony and rod and dividing bacteria. So that's it. Thank you.